My name is Jakub Kozłowski. I come from Poland, and I'm very delighted to be here. I was very surprised when I got the opportunity to speak here. Of course, if you have been to yesterday's after dinner speech, you know what it looks like when you get the offer. You think about it for a long time, which took me like 4 seconds anyway. So thanks to John and everyone who helped him for the conference. It's been really great, full of surprises and a lot of fun, and I hope you have the same experience and you'll enjoy this talk and the rest of the evening. So today I'm going to talk about streams. There's the word compositionality in the title, so compositionality will also be mentioned in a part of this talk, but we are mostly going to talk about functional streams. So what does it mean for something to be a stream, and why do you even care? So a stream in the most general, or maybe the Wikipedia definition that you can find, is a continuous source of some sort of data that's coming from somewhere, a magic place that you don't want to look at probably. But these are just one kind of streams that we can encounter in our lives, the infinite streams. But not all streams are like that. And we can encounter streams in different situations in our code or our life, because our code basically just models our life, right? For example, yeah, I'm sorry, this is the third slide, and there's already some code. But for example, we can traverse a list multiple times, just make a call for each element of the list to find something, then maybe find something based on that, basically recurse on some structure or do pagination, like lots of things. So in this case, let's say we're working in some sort of imaginary GitHub API or something like that. And we are doing just that. For each element of a list, we will run some I/O, then some I/O, and we will have to flatten all that. So you can imagine in a functional piece of code what will be used. There will be flat map, there will be traverse, and, well, many occurrences of each of these. And that's fine. But the situation may become more complex. We might have to do pagination. So after getting a page of elements, starting with like after project equals none, we will get this page of results, and we are going to use the last element of that to get the next page, and so on and so on. But we don't want to keep doing that until we exhaust the whole list. We just want to do that when we until we find the first issue that matches a given predicate. So we cannot just do flat map and traverse and recurse and then filter and only stop at the element that we are looking for, because we will unnecessarily traverse the whole list and make a bunch of calls that maybe just one would have been enough. So this would be slightly more complex to write than the first example. And then there's something completely different, listening to events coming from a queue or a UI from in like Scala.js or something like that. You might be listening to events and reacting to them in a certain way. That also sort of represents a continuous source of data that you need to handle. And there are many other cases in which you can have a stream of data that you don't really maybe think of it as a stream, like an infinite stream, but you can basically reason about them in the same way as with the previous examples. There's some incoming data from somewhere. You want to do some operations on it, on that data, maybe stop at some point or change the way you are doing that based on what you got in the data, and go on. So there's a bunch of stuff like TCP connections, HTTP calls. All of these, well, many of these will be hidden under a certain abstraction, like a scheduler of jobs to be done by your application, or an HTTP client that just allows you to give a request and get a I/O of a response back. But in the end, all of that is sort of based on, or can be based on streaming. So all of these examples have a common core, or at least we can look for a common core. First of all, we can make control flow decisions in some of these cases. For example, in the pagination example, we want to stop at some point, and we don't want to keep traversing the lists and expanding our state of what we found forever, or until we exhaust the source. We just want to do this until we find something that's of interest to us. Then we might want to add parallelism to our pipeline or process, whatever you call it. And we could do this on each step, or maybe we want to have like a global amount of parallel actions that we want to be executing and no more at a time. We also have effects, like a lot of effects, because pretty much every call to this paginated API or this, basically whatever we do while handling events will involve effects. So that's another thing that was common in all of these examples. Then we have then we have handling multiple values, because we will always work with like either an infinite stream of events, or in the other examples we had sequences of projects or issues or whatever. And some of these will require us to deal with resources, like the listener of events will probably have to start some sort of client to some sort of queue or basically external system, and these resources need to be managed. We need to clean them up after we are done using them, especially if you're not doing that once per application, just maybe once per HTTP request or in your tests. This is really important, that you can run your tests, and after that is done, all the stuff that you started and set up is then cleaned up. So is there a common core to all of that? And we can come up with a common core, and there are already solutions for that. One of them is a library called FS2, which we're going to talk about for the rest of the talk. I'm sorry. But I hope that at the end, you will realize why I decided to focus on it so much. So the core abstraction of FS2 is stream, which is a data type parameterized by two parameters. There's a higher-kinded type f, which represents the effects that will happen in our stream. And there's a normal type parameter, O, which is the type of elements which will be produced or emitted by that stream. And a stream is an immutable lazy value, which means lazy as in when you create it, it doesn't do any effects, actually. It will only happen when you compile the stream to some sort of effect that you can then run, and that will actually execute all the magic that you want to run. And a stream, at least in FS2, which let me recall that we are going to talk about for the rest of the talk, it can emit any number of values. It can be 0 values. This is a perfectly fine use case. You can embed any sort of effect in a stream, and you don't always want every effect to produce a value. Or it can emit a finite number of elements. For example, if you wrap a list in a stream, then that's a finite amount of elements. Or it can be infinite. For example, if you're reading events from an external source, that should never, ever run out of messages under normal conditions. Like even if you are listening to a Kafka topic, eventually some more messages will come, right? So it will never actually end until you, for example, shut down the broker, but then your stream will fail with a throwable. So that's two things it can do. It can produce values or fail with an exception or any sort of throwable. And a stream of f can have effects of type f, which is usually I/O, some sort of I/O. I don't care which one. Or a less formal definition, if you don't like this one, it's a description of a series of effects producing values. And because it's just a description, it doesn't run anything. Let me just recall that. There's a special case for streams, which was actually mentioned on Guillaume's talk yesterday. These are pure streams. And pure streams can be evaluated to a list or just ignored. We can run them without collecting any values, but the simplest use case is probably just collecting the elements to a list. And that doesn't have any effect. It's guaranteed in a type. And that way we can just convert a stream to a list, which will start all the actions that we've embedded in our stream and collect what it's going to emit. And that works thanks to a clever hack, which is a type member, an abstract type member that's a subtype of nothing. This is really crazy, and I still don't understand it, but it's also really cool. And that also is made possible by covariance of the actual stream type. So a stream of pure is actually a subtype of any stream of with the same output, right? So that works for any f. All right, so I mentioned streams. There was an example of a pure stream with just stream 1 to 3. That's one way of building a stream. It's not terribly efficient, and it also works with just a constant amount of elements, right? Or a list that we destructure. But there's plenty of ways to build a stream. We can, in the simplest case, we can lift a single value. We can lift a sequence of values, any sequence of values. Or we can lift an effect that will produce one value. And these are all finite streams, right? So we can run them and they will eventually complete pretty fast, I assume. Unless, of course, this effect runs forever, which is a perfectly fine use case as well. But there are also infinite streams, which I've already mentioned. For example, string constant will emit an infinite amount of 42 in this case. And we can still run that stream as a pure stream if we first limit the amount of elements, which will be mentioned on the next slide. We also have stream every, which will emit a value. Actually, it will emit the amount of time that has passed since we run it every second in this case, because I use 1 second. And that's, again, this will be an infinite stream that we can limit later or use in combination with another stream. And stream iterate is the same thing, except it's still a pure stream, which we can limit and convert to a list without any effect. So I mentioned limiting streams. So there are plenty of ways we can make sure that a stream, when we collect all the values in it, doesn't blow our memory. So one of them is drain. It will remove all elements from a stream, which is, again, a perfectly fine use case in some situations. This head, which will just take the first element if it is there. The take, so just the first 10 elements. So an infinite stream plus take will just give us a finite stream, which we can work with in a variety of ways. We can also stop a stream after some period of time, or we can stop one stream when another stream produces true. Or we can just use a single effect for that. To consume a stream, an effectful stream, with, for example, something like I/O, we need to compile the stream to the effect that underlies it. And if we follow the completion in an editor, we will discover a variety of ways. These are just 3, and there are more, but probably the most popular. So we can drain the stream. Again, this removes all the values from the stream and just runs it. So when all the values are emitted by the stream, we will get a single unit in the result eventually after this I/O completes. We can also get the last element of the stream or gather all of the elements, but this is pretty dangerous if you don't know what sort of stream you're working with, or if it's obviously an infinite stream. All right. So now that we know how to create a stream and how to run it, how to compile it to I/O, which we can pass to our I/O app or the runtime of the I/O monad, basically, let's look at how we can transform existing streams. So for the purpose of this example, I have a stream of random integers. and a function that will allow us to print an integer in an effectful fashion with I/O. So let's look at what was happening here. We start with a stream of numbers, which we then transform element by element using map. The same abstraction that we had with list and array in Scala, or basically any sort of sequence or option. So basically any sort of functor is the same abstraction still. Then we flat map, which is again the same abstraction that we've seen so many times with list, I/O, option, all of that. So we replace every element in the original stream with a new stream, and then we flatten that structure so that all the elements produced by this new stream will end up in this new sort of flattened structure. And at the end, we run an effectful function for each of these elements. And all of that is sequential. By default, there's no parallelism here. Like, if you want to run flat map or eval map in parallel, like have 10 elements being concurrently effectively transformed, then you need to use par eval map or map async with an explicit concurrency level. So what this looks like when you actually run it, let's imagine we had a stream of random numbers that produced something like this. Then after the map, it will obviously be single-digit integers, well, potentially negative. And then all of these elements from this range, from 0 to the current element, will be put inside one big stream in the order that the original elements came. And if we were to use an imaginary operator for debugging, this would just print every element at every one of these three stages highlighted. We will see what actually happens under the hood. Like, what happens? Do we actually map all the elements first and then flat map them first before going to the next stage? Well, that's not actually what's happening. This is the approximate output for the previous data that I showed. So let's add some color to it. And you can see that the stages interleave. So first we process the first element, which only gets to stage 2 to map, because well, it actually enters the flat map, but that flat map doesn't produce any elements because a range from 0 to a negative number is empty. And then only the second element, which we can focus on for a while, it goes through the whole pipeline. So it will go through map, and it will produce some values into the flat map, all of which are going to be eval mapped with show out. So these are the violet parts of it. So what's actually going on, we are not traversing the whole stream, the whole sequence of values eventually produced by the stream in a sequence. Like, we're not mapping them all first and then flat mapping them first. We do that on an element per element basis. Or we can do that on a chunk per chunk basis, because sometimes that's just more efficient. So it's really good to realize what's going on here. And this is what actually makes all of this short-circuiting possible. If we were to create an infinite or very long stream out of a pagination result, we can build it up and map on it and filter on it and maybe take 5. And that will, at that point, we'll only just take 5 elements, and everything that would have been after that, we'll just not touch that. If I were to take 2 after this flat map here, then I would never, like, the part after the highlighted one would never happen. I would just stop after 0 and 1. Right. So I mentioned we can use streams for control flow. Let's look at an example. So here I have a single element stream that encapsulates a resource. So we define how the resource is going to be acquired using the bracket operator, and we define how it's going to be closed in the second parameter list. And I'm going to use this stream in a slightly more complex stream. I will use this resource for that. So let's again look at it closely. First, I have a stream that produces 3 elements, a constant amount, and these are constant values. Then I concatenate that to a stream of random elements. Altogether, they will provide up to 5 values. And then we will run a stream that will just wait for 200 milliseconds once, and then use the file resource in a stream and read lines from it until we're done with the file. And then I guess we get each line's length. And this is a stream of integers. Like the whole thing combined is a stream of integers. And when we run that, we're going to, if we run that and use something like showLines std out to see what's going on, what values we get, we will see that we instantly get a couple of values, all the constants, all the randoms. Then we have a short break for the sleep. And then we have the resource gets acquired. The file is opened. We read from the file. And then no matter what has the file, even if we get any errors, the file is closed. And if there were no errors, all the line lengths will be produced to the output. So they will end up in the result of the whole stream. And we can push this to the extreme, really. We can build very complex stages, very complex behaviors using streams. Let's imagine we want to build this operator that will produce values, finite durations, units, ints, whatever. It will just produce a value that we will later discard. And you're going to see why in a second. But the behavior of it is supposed to be like this. It will emit 10, actually n elements very quickly, 1 millisecond between each element. Then it will double that duration and do it a bit slower. And it will continue to slow down exponentially every time it goes through through n values, unless something is produced by this reset stream. So if something is produced by that stream, we will reset the duration between elements back to 1 millisecond. So we can start with the delays, or basically the base building block. We will come up with a stream that iterates through durations from 1 millisecond to 2 milliseconds for exponentially. And then for each element, for each duration in that stream produced by this iteration, we will create a new stream that wakes up every duration, produces n elements using take, and then it prints a message that, hey, we are slowing down. Then we will create a new stream using some state and mvar for synchronization, so something that will semantically block until there's an element in it, and when we read from that, it will semantically block until there's an element. And when we try to put something in there, it will semantically block until there's no element. So here, we take that stream that we just built with the delays that grows exponentially. So that would just slow us down forever without any way of resetting that. We will take it, and we will stop it when there's a value in this mvar. Then we will do that in repeat, and concurrently to the stream, we will do something else. We will use the reset stream, and every time it produces a value, we will try to put a value in this mvar. Since it's just for synchronization, I can use unit here, so that's what I'm doing. And then I will show resetting delays. So the whole thing looks like this. And if you think about it, this is a pretty complex problem. And if you wanted to support all the edge cases of concurrent access to it, and if you wanted to work with any sort of stream that will produce values very fast, and you wanted to slow it down, then without something like a functional streaming library, this would be extremely time-consuming, annoying, and bug-prone. So let's see how you would use it to slow down another stream. There's an operator called ZipLet on stream, and it will basically zip these two streams together the two streams on the sides of this operator, which will mean that all of these streams, both these streams, will be combined into one that will produce a value every time each of these streams produces a value. So it basically slows down the slower stream. And in this case, let's imagine client messages is coming from like a WebSocket or just a global event bus from somewhere. So we will reset the timeout between the slowdown every 3 seconds. And after every 5 messages coming into the client messages stream, we will slow down. So I guess this is time for some demo, because I think you've had enough code for a while. So let me quickly do something with this. OK, I hate displays. Come on. OK, this is not what was going to happen. Right, so let me use this. I have an example with a TCP server. So this is what messages will come from. I will start a TCP server, and for every connection that gets made to this server, I will just read everything that the client has to say. I will decode that as UTF-8, then convert it, split it into lines, and print each line as message, and then line text. And I will allow up to 10 clients at the same time. So here you can see this client messages stream that comes from that. I zip it with slowdown. Actually, I didn't finish. Zip left zips these two streams, but only leaves the values of the left stream. So it basically slows it down if the second one is slower. And it is pretty slow here. So let's see how that works. I will run that application. It's running. And now let's open Telnet and send some messages. So you can see that the messages appear in the server. But let's actually see if they are being slowed down. So I will produce a sequence of elements and send it as a netcat to my server. And you can see that it slows down every 10 messages, because that's what I had configured. And then it speeds up again every 3 seconds. So it works as predicted. I think this is pretty cool. And thank you. And we can do even more. Like, this is probably a bit crazy, but we can find all the source files that I have, and I can send them and see them in my application. Also slowed down. Like, this is probably the only practical thing I can do with this. I mean, this is of course useless, but it's fun, right?
Is this a Scala compiler?
No, it's actually all the examples. Spoiler alert. Yeah. Anyway, so the sending is done. The application is done. The delays are reset. Right. So I think this is the most interesting part of it. Right, and let's get back to the slides, actually. We can do more demos later if you guys want. But yeah, that was the demo. The important part here is that the slowing down of the stream will sort of propagate to the very end. Like, FS2 streams are pool-based, so it means that we will only get messages in our hands, get items or values in our hands if we ask for more. So in the case of TCP, the TCP support of FS2IO, which is an FS2 component, they use basically, I think everything that's a TCP server will use a buffer for incoming messages, incoming data, bytes. So if that buffer is full, we will just not ask for more elements. So I couldn't reproduce that with TCP, but I didn't want to pull in another library to show anything else. But if this were something like HTTP calls, and someone wanted to upload a file we could sort of slow down that stream every time they sent a certain amount of bytes. And that would also back pressure them using the whole TCP back pressure mechanism. I just wasn't able to reproduce that. But yes, it works. So you get basically back pressure for free, unless you do something like unbounded queues in your application, which you should never do. Right, so another cool thing about FS2 is that, or functional streaming in general, this will work with ZeroStream as well, I think. You can sort of invert the flow control that you were given. Like the original solutions for flow control, actually, I don't like this slide, but basically we can move the decision on when to stop doing something out of actually doing something. So if you don't see what I mean, we had this example before, like finding all the issues in all the projects that have something. So we don't want to execute this, we don't want to find the issues in projects that are excluded, right? And let's imagine we have another use case for the same data, like finding the first issue in the first project that matches the given predicate. So normally, if you wanted to implement these two, you would probably have to repeat yourself quite a lot, because you need to use a different stopping logic for determining when to actually stop. But you will have to repeat the way of finding the next page and the next page and so on. So we can actually factor that out. We can create a stream of projects and then a pipe, which I will explain in just a couple of seconds. But we can extract these parts. They don't even have any dependencies here. So they don't depend on what exclusions we have or what the predicate in the second function is. And we can reuse these two parts in these two implementations so that we don't have to repeat ourselves for the whole pagination thing or whatever that is, or whatever our data is coming from. So I think this is pretty cool. Now, what the hell happened in this slide? Yeah, so this is the implementation for the second function. And pipe. Pipe is a really nice abstraction. It's really nice because it's so simple. This is just a function, like a type alias for a function, from one stream to another with the same effect. And pipes are really cool because we have an operator called through that allows us to just pass a function. And instead of building custom operators for streams like extension methods, we can create functions or vals and create pipes out of them and just pass them to this through function. And it composes really well. It solves all my problems with extensions. And I think more libraries should use such an abstraction. So these pipes you can think about them as reusable transformations. And they can do things in an element by element basis like I do here. So I execute an effectful function for each element in the first one. And then I only collected the elements that were wrapped in sum, in a full option. And in the second one, I map each element to the result of decoding using CIRC. And I only collected the ones that were full again. But pipes can get much more complex than that. They can carry state while we are processing something. And I actually have a demo for this, but I don't want to switch too often, so we can get back to this later if we have time. So the compositionality aspect of it. What I mean by compositionality is if we can understand an expression by understanding its parts and the way they are composed together, then that expression is compositional. And what this means in the context of I/O, for example, and referential transparency, is that this is a program that will, like in this example, it doesn't have anything to do with bracket or forks or commits at all. We just have two actions in general in this example. We create a fork of a repository in the GitHub metaphors, right? We then try to commit to the repository some data A, and then regardless of whether that commit succeeded or not, we will close the fork or remove the fork. And this is the first action that we are doing. Then we have a second one, sending an event. And because I/O is referentially transparent, we can split this into two smaller programs, which we then compose using the and-then operator from flat map syntax. And what's really cool about this is this is the same program. It doesn't send an event before committing, or even if I reverse the order of prog1 and prog2 definitions, it will still behave in the same way. So I think this is really nice, and it really helps in understanding a foreign piece of code if you can reason about it in this way with referential transparency. If you can just inline or extract parts of code without worrying that you will actually get a different behavior and that you will misunderstand what's going on. And it also allows you to name things that would otherwise be defs without functions, without arguments, or with an empty argument list. It doesn't really matter if you use a def or a val if you have referential transparency, unless you're doing recursion. But I want to focus on this part, the bracket. So referential transparency gives us a certain degree of compositionality, but it doesn't give us all that all the superpowers. For example, here, what if I wanted to do something more with this repository while it's still existing, this fork still exists? For example, I could extract it out, abstract this away and allow the user of my function to provide the way that they want to use the repository with. But that is still not enough, because what if I want to run a stream using that repository? And what if that stream is, well, very long, and I don't want to run all of it before the repository is closed? Before this I/O completes. If I did that, if I just consumed all the values of the stream and kept them, well, this wouldn't be a very, very fantastic day. So we can do something else. We can lift this bracket. We can lift this temporarily resource to a stream using stream bracket again. And then we can append an action that will run after this bracket is closed that will send the event. And then the user can just use our stream and flat map it and do whatever they want in that flat map. So streams sort of encapsulate we can encapsulate resources in them, but still allow us to work with them in any way we want. So I want to talk about testing for a quick while. How would you test this function that takes an I/O? So you don't really care while testing what the actual I/O does, the one that you pass in. You don't even care what it will produce, because it's abstract. It's parameterized with a type parameter. So all you need to know is that if it completes, then your whole result will also complete with the same result and 42, right? If it fails, you also probably want to fail. So that's pretty much all you need to test for. So you don't need to handle any different cases of whatever the I/O could produce. And we can do the same thing with stream. And this is actually pretty cool. So here, let's imagine this comes from my source code, from the very inside of a deeply nested function. I have a source stream that I filter on, and I will probably return that. Then later, in a different function, I will probably consume that, keep it running, or compile it and take all the elements as a list. But I don't need to know that when I'm testing this part. If I want to test these particular two lines, what I can do is I can move it out of my deeply nested function, just take an argument, which is the stream, or create a pipe that would be the same thing. And then I can test it, giving it any stream that I want. It doesn't even have to be an I/O. If I'm doing something concurrency related or something resource related, something that has effects, in that thing that I want to test, then of course I will need something like I/O, and I will have to construct an effectful stream to test all the edge cases in my tests. But if this is a source, for example, from Kafka or from a file or whatever else, I don't need to know that in my tests. I don't need to know that in my implementation, so why should I know that in my tests, right? So I can provide any sort of effectful stream and sort of mock the behavior that I wanted to have using simple operators like stream raise error, which will just be a failing stream, or a stream that produces some values and then fails, or a stream that takes very long to complete. I can sort of test all of my edge cases without actually connecting to anything. And I think this is really cool as well. So FS2 is truly compositional. Like, believe me or not, if you work with it for a while, you will love it. Like FS2 or any other functional streaming library, if you see one, is going to be a pleasure to work with. Just because you don't need to care about so much stuff while you're working with them. You have a single abstraction for basically an infinite amount of use cases. You can have very small data. You can have a finite amount of data, and you can have infinite data, all in the same abstraction. And all the operators, all the combinators that you build for that are going to work across all these streams as long as they support the types that you have in the output or whatever. And it's a single abstraction that scales from very small, very short, pure streams to the most complex processes that you can define with lots of resources and concurrent things. Like you could expand that to queues. FS2 provides queues, which give you a way to push elements from a stream and take elements as a stream. And you can run that concurrently and sort of create an echo server or a load balancing thing inside your application. The possibilities are just endless, and you still work with this one single type that does all the work for you. And if it still sounds like you want to just use list and I/O, well, this gives you all the powers of lists and I/O and much more with far less responsibility, because now you have the option to stop early without rewriting all your code for that particular condition. So here's another example from the main website or README of FS2. This is one that I really like. We can see all the stages in the pipeline, and yet there is some logic deeply hidden in the way, for example, that the text line pipe works. Like, it's not an element-to-element basis because there is a stream of text, and we sort of that pipe basically splits that so that we don't have to handle this in our code. We just have this clean compositional API on top of it. So every stage is just pretty much one line, and we can build operators like that on our own, and it's not really hard. This is the code for the TCP server. This is all I had to write to listen to messages sent from TCP. And it's not really a lot. And you can reason about each of these pieces in separate. And it really is a very composable or even compositional, which is more powerful structure. It just gives it so much power. There's plenty of projects using FS2, so if you want to integrate with some external services of other systems, there's quite a lot of that. It's still not complete, and there's still much more to do. So if you want to learn FS2, for example, you can start by building your own integration with something else. There's even a conversion to and from Akka streams. So if you insist on using Akka or you are using a technology that only has connectors for that, then that's the way to go. So I encourage you to give it a try. It's a really nice library, as I've probably said hundreds of times already today. And this is almost the last slide. I want to thank Fabio for helping me with this talk and answering actually hundreds of questions on Gitter. Like, if you have any questions, you can probably ask him. Or me, yeah, I guess. I guess you can ask me. And thanks to everyone who contributed to this library and all the others that are it sort of builds on. If you've been to Fabio's talk yesterday, Cats Effect is like a really nice core of this all. And FS Studio is built with Cats Effect like everywhere. And all of this would not be possible if not for the work of hundreds of contributors. So I want to thank them all. And the same goes for Cats. Like, this is a very solid foundation of this all. I encourage you to watch these two talks by Runar and Fabio. Yeah, basically that's it. So that's pretty much all I have. Thank you very much.